Man, I am impressed. You guys look, and ladies look pretty refreshed for being here for 4 days. Getting tired? All right, I'm impressed you folks are here. I'm tired, but I'm also excited. So welcome to Red Teaming Windows, building a better Windows by hacking it. I'm gonna sort of open the kimono or show you how we make the sauce or any other number of kind of cliche discussions about how we actually go about securing Windows and how we select various security features to build into the platform. So my name is Dave Weston. I'm a group manager in the device security group in Windows. But I also, besides from building kind of advanced security features like application guard, virtualization-based security, various exploit mitigations, I also run the Windows Red team, who has a really fun job of just building a bunch of exploits that we learn from on a daily basis. And so during this talk, I'm going to show you how we use this Red team or this threat simulation process to build better protections in Windows, to learn more about our incident response processes and tune them, and then of course to build detections in products like Defender and Defender ATP. So that's the basis. So the first thing I wanted to comment on, I love Ignite. Coming here is always interesting. So I'll meet someone and I'll start talking to them about, hey, have you enabled this virtualization-based security, this hypervisor security feature? And they'll bring me right back down to earth. They'll say, I need help patching Win 7. So it's always useful for us Microsoft people to hear this, right? Because I think sometimes we're just out in space, I'm looking at APTs in 0 days. Elia's like sending me the latest, targeted 0 day. We're tearing this thing apart. We're building a hypervisor to isolate it. And then we come here and we realize there's some other problems that we have to take care of first. So that's helpful. But this will be a glimpse of kind of the future of things to come, and you'll see the direction in which we're heading. So without further ado, I'll jump into that. So this is a chart I generally show when I want to talk about how we are doing. So metrics are really difficult in security. It's very hard to measure security, and even these metrics, honestly, I could go on all day about caveating them. But I wanted to talk about them to explain the way we think about measuring how we're doing and how we're delivering for you, the customer. So this chart on the, I guess it's your left-hand side, is the number of vulnerabilities that we see in the Microsoft ecosystem every year. And one of the things that you'll notice right away about this chart is it's sort of growing linearly, right? It looks pretty terrible if you look at the chart on the left. More vulnerabilities in the traditional sense means more risk, more scary, you're doing worse security-wise. Now, the chart on the right is interesting because it tells a pretty different story. It tells the story of how often those vulnerabilities, which can be thought of as potential risk, are turning into actualized risk, which is somebody's actually taking them, writing an exploit for them, and deploying them against a target. And that is dropping dramatically. And that's sort of interesting, right? Because when we think traditionally, again, about how we would measure a product, you would say, more vulnerabilities, the worst, right? Every Patch Tuesday, I see a blog. 5 gajillion vulnerabilities in Windows, the sky is falling. And it's really important for you folks to understand that while taking vulnerabilities away and addressing vulnerabilities, and especially finding them before you ship a product, is absolutely critical and part of the fundamentals, it isn't the only thing that we measure ourselves on. What we actually measure ourselves on is, are those vulnerabilities turned into exploits that impact the customer? And this entire talk will be about how we evaluate our ability to prevent vulnerabilities like this, which just realistically are always going to exist in complex systems, how we make sure those things stay potential risks and how they don't become actualized. So the kind of story of the way Microsoft has approached security is the story of preventative security. So how many of you have heard of the Microsoft Security Development Lifecycle, or SDL? All right, some hands. So SDL was revolutionary for its time. It was really instituted around 2002, around the time of Slammer and Code Red and these wormable flaws. I thought we were behind those times, but WannaCry might have suggested something differently, but we'll talk about that. But this was revolutionary for its time because there was essentially a stand-down at Microsoft for a period of months where all of the engineers did nothing but focus on security. And the approach that they took at that time, which seemed pretty rational, was let's start, before we write lines of code, let's evaluate the design, what's called threat modeling. Let's see if there's any issues in it. We'll apply a attacker model to that design. We'll see if there are any flaws, and we'll address it. The other thing that it did was focus on, for each individual component, and right, at Microsoft, every team kind of owns a separate component. You'll focus on trying to find vulnerabilities and get rid of them. But the real goal of the SDL and preventative security is don't ship software with bugs in it. How many of you think it's possible to ship complex software without bugs in it? I'm not seeing many hands. So, well, it's a good strategy when we step back, 10, 15 years in the future. We're like, that's pretty interesting that we put all our eggs in that preventative security basket. That's also why I think that metric and the people that sort of put a lot of stock into it are a little bit out of touch. The other thing that the SDL did is it really sought to integrate security in the development process, which is cool. It means that hopefully components are born secure, that a lot of thought is put into it. But with that sort of integration and engineering came a lot of process. And sometimes when you build an abstract model, you sort of get away from what you were actually trying to accomplish to begin with. So pretty soon, Team X is building a secure component, Team Y is building a secure component, but when you put them together, they're not really working out. And so attackers don't really look at components the way you do from your organizational structure and processes. They look at, how am I going to pwn this thing so I can do what I need to do, steal credentials, steal data, et cetera. And so we really needed to augment preventative security for a few reasons. The first thing we need to do is figure out, how do we modernize our security processes so that it's agile like attackers are? I mentioned this in the security keynote, but I think the reason you're seeing this upswell in attacks is really because attackers are driving innovation in a lot of ways much faster than defenders are. And for this very reason, right, where defenders are very process-oriented in general, right, this is a general statement. It takes a longer time to turn the ship around, so to say, for defenders, where attackers can be 2 or 3 person units. They can move very quickly. They have very little restrictions on what they can do. And so if you're applying this sort of big, slow, process-heavy, bureaucratic model to security, you're just going to get run around by attackers. The other problem with preventative security is it doesn't make sense economically. So today, if I find a code execution vulnerability, potential vulnerability, not an exploit, in Google Chrome, I can get $7,500. $7,500. Sounds pretty good, right? That's not bad. What do you think an exploit in Google Chrome costs? $150,000 to $250,000. So if you're focusing on the most fungible, the cheapest part of that economic chain, you're sort of focusing on the things that attackers care about the least. So the thing that I wanted to figure out is, how do we drive more cost? How do we disrupt more for the attackers in the places where they're doing things post vulnerability, not focusing on the vulnerability? Here's another thing, is a lot of the security model previous in Windows was abstracted from the way things were used. So rather than looking at, hey, attacker X has exploited us 20 times with the same library, we should think about how to break that library. And I think especially when it comes to, let's call it mature attackers, potentially state-sponsored, the attacks that you see in the news, what we know about that is that they largely operate like any other development company. They're 9 to 5, they come in, they do a git pull, they send out a code review, they do a merge. It was a bad merge, they got to roll the merge back. Their Jenkins server is, it's regular software development. And what does that mean? They're building reusable components. They've got their coding styles, they've got their preferred targets. They're really good and efficient at those. So when you break those templates, when you break the things that maybe they spent 2 years R&Ding, you tend to disrupt them, and they go away. And so being able to focus on those and make sure that the types of technologies we're bringing into Windows to protect people are actually causing the attackers damage and making it essentially more expensive to attack Windows is critical. And the SDL didn't do that. And then the final piece is we'd find a bunch of bugs. We had no idea if that was all the bugs. How could you know, right? You're like, I found 100 bugs. Is there 1,000 there? Is there 5,000? Is there 101? No idea. And the other issue is you could be 98% effective. You could find 98 out of those 100 bugs. It only takes 2 to set the world on fire, right? WannaCry, NotPetya, the internal blue stuff, we're talking about 2 or 3 vulnerabilities. So we as Microsoft, I can tell you, because I worked on this, we fuzzed the crap out of SMB. We slammed it with code review. We did everything to that. I think we actually did a pretty good job, but it only took 1 or 2 bugs to miss for things to go bad. And I'll tell you a little bit about the story about why, at least for some parts of that, there's actually a silver lining there. But the point is, we need to move away from assuming we're going to prevent everything to assuming we're going to get breached and then focusing our engineering resources there. So the way we did that was pretty straightforward. It wasn't the most elegant, but it was effective. So what we started doing, moved away from just fuzzing, just code review, just trying to find all the bugs, and we started analyzing what attackers were actually doing. And I call it zoology. Why do I call it zoology? It's kind of a boring job. It's like research. So we'd take an exploit, we'd tear it apart, we'd record, this was a buffer overflow. This was a buffer overflow in component X. This was version 5 of component X. The buffer overflow was in structure Y. We'd gather gobs of data. And the reason I call it zoology is it's a lot like the zoological studies that I'm familiar with, which is the chimpanzee crapped at 1 p.m. At 1:13 p.m., they ate a banana. And then what you see out of that, though, is this amazing study about the characteristics of chimpanzees. So that's kind of what it's like to do, right? It's like research science. It's really boring and to some extent, but the value and the insights you get out are incredible. So we'd power these analysis where we could see things like 90% of the exploits in Adobe Flash are focused on this one type of vulnerability. Aha, that's a great place to invest, right? It's a lot better than stabbing in the dark and just hoping that you're going to understand that. Then the second thing we decided to do was start having our security engineers build the protection features. Prior to that, we would design a feature and we'd say, oh, great, kernel developer, will you please implement this thing? And of course, the kernel developer is dealing with reliability issues, performance issues, battery, any number of things. And so getting the security engineers to turn their ideas into actions got us a lot closer to what attackers are doing, which is this immediacy, this agility, and those types of things. And that is absolutely critical. So we build the features. And then the third piece, which is basically the rest of the talk, is evaluating it. So we set up a red team to do the evaluation. And this is pretty interesting, I think. I never, when I start to set up a red team, I actually didn't think management would go for it. So we've had red teams at Microsoft for a very long time, but they're sort of the classic network penetration test teams, right? Scan for open configuration issues, passwords, known vulnerabilities, assess that, pivot into the network, and then sort of deliver a report. Configurations get fixed, security improves. In the software world, we didn't have that accessibility, right? The people that can do that are a pretty small number, right? Look back to those exploits, about 10 exploits written a year, and the vast majority of those, let me tell you, those are coming out of state budgets, right? So this is a very big endeavor. So we set out to build a team who could replicate that, and the goal was really for them to challenge those defenses we built in Pod 2 in the same way attackers would, because what we were doing prior to that was we'd build number 2, we'd ship it out to y'all, and then wait to see what happens. And sometimes people would get exploited, and we'd learn from that, and we'd rinse and repeat. But having that, again, this is all about a short cycle of build to deploy, is having that internal team who can basically just take the code and start attacking it at the level of kind of a state-sponsored adversary was crucial to improvement. So the multidimensional analysis phase, whoa, I'm getting like alerts. The multidimensional analysis phase was pretty interesting. So we take from a whole bunch of sources. So the first source is telemetry. So we detect exploits. We track, I don't know, Elia, how many attack groups do we track at this point? 100? Probably 100, very active adversaries we track through telemetry. We watch for them. We watch for new tools they might be using. And we will take that information and process it. Of course, Microsoft, also happens to be at the, the center of a lot of vulnerabilities. So we get a lot of things reported into us and exploits, so we're able to tear those apart. We've got threat intelligence partnerships with every security company under the sun, and then we've got automation for scraping social media. So the next time a security researcher posts up a new technique on Twitter, that's usually being automatically consumed and then put into this structured database. And of course, we've got our internal efforts. But this is where that chimpanzee poop sort of gets processed. It gets turned into a set of reports that we can do an analysis on, and then that's how we decide to build things. So let's look at how this worked in practice. So Adobe Flash, pretty good test case, right? Adobe Flash hasn't always had the best security reputation. I love the people at Adobe, work with them all the time, but it hasn't had the best security reputation. I love working on projects like that. This is the person who ran Internet Explorer security, so I can take a lot of tolerance for pain. And so one of the things we did in the Flash exploit space is we did this analysis. And you see some of the results of that in this chart here, exploit techniques used in published Flash exploits. So public 0 days, we took a 2-year span and we broke them apart. And so one of the things you see in that top chart there is 85% of the exploits, and I don't remember the absolute number there, but 85 of a couple dozen exploits all used one technique, which is vector length corruption. That's a fancy way of saying they corrupted a particular field that allowed them to get read-write of the entire memory space from ActionScript. Not a good day. The other thing we noticed is that there was a prevalence of a bug type called linear heap corruption, which is just a fancy way of saying a heap-based buffer overflow all over the place. So we're looking at these two mitigations, and lo and behold, if we focused on those two bug classes just as a start and did nothing else, we would have an impact on something like 95% of Flash exploits from 2 investments. So we did that, and I didn't actually get a chance to generate all of the numbers, but I think you would intuitively say in the last 12 months, I can only think of maybe 1 Flash 0 day. And this was for a product that a lot of people had said, it's impossible to secure. I'm not saying it's even secure today, but I'm saying that using this type of methodology, we're able to empirically improve it. And this actually came from our learnings, like I said, on Internet Explorer. We did the same thing. When I took over Internet Explorer security, it was right after that sort of string of magenta things. That string of magenta things is 4 0 days in a month time span. And when I took over, it was just after the DHS had said, stop using Internet Explorer, use Chrome, use Firefox, just don't use that. So it's a bad day for Microsoft. Take hit in market share, that's hits to revenue. And so what you see in the green is, rather than responding with that conventional approach, which was more fuzzing, more of the same, more of this, we started in Patch Tuesday updates shipping mitigation. So things very similar to what I showed you there, which is we started targeting bug classes with use after free protections. We added control flow guard, which targeted return-oriented programming techniques. So rather than simply fuzzing or waiting till the next version of the operating system, we started aggressively shipping mitigation features to the world. We had never done that before. We'd never shipped these types of features in a Patch Tuesday update. So the attackers weren't ready for it. So not only did they lose a lot of their 0 day exploits, but their stuff starts crashing. It starts not working on customer networks. They're all spun up. They've had this sort of luxury of having the same tempo all the time. Now we can track them better. So we went from a pretty substantial number of exploits in 2013 and 2014 to, I think we dropped from 156 days of 0 day exploit exposure. That means 156 days where there was a 0 day exploit in the wild we didn't have a patch for, to 45 the next year. So dramatic change. And a lot of that is attributed to this approach. So what we established through the exploit zoology is we can have a lot of effects if we focus on breaking attacker techniques instead of just trying to find all the bugs. So then it became the question of how do we do that more efficiently? And so at this time, our process was basically wait for exploit to occur in the wild, do an analysis of it, and then fix it. That's a decent approach, except that it requires people to get owned, which is not the best, right? So how do we do this without people getting owned? And we looked at our friends over in the cloud services group, and we were like, they're doing something interesting. So they declared, actually several years before we had this idea in the cloud, I think they were pretty visionary, we're just going to assume breach, and we're going to have all our blue teams looking through Azure Security Logs, O365, security detection systems, and we're going to have the red teams every day of the week just pounding on our services, and we're going to see how fast we can find them, how fast we can contain them and remediate, and then we're going to set KPIs based on that. So they were out of the preventative game a lot earlier than us. And so we said, oh, maybe there's something to this. And so we set up, like I said previously, a red team in Windows and devices. And I think the interesting part of this red team was, again, rather than doing sort of the conventional services stuff, these folks just wrote zero-day exploits. That's their entire job. The way I describe it is, are you folks familiar with the pwn-to-own browser competition? Every year they put up all the browsers, and teams from all around the world go and hack them, and it generates a big news cycle. We actually got a ton of value out of that competition because not only would we get hacked, but we had the chance to get in a room with the people who hacked us, and in between them making fun of us and chastising us, they would tell us about what they did and how to improve. And so the way I describe it is my team, the offensive security research team, is just doing pwn-to-own every day. And trust me, they love their jobs and they're pretty good at it. But that gives us a few things. One, it gives us the ability to model real-world attacks. Number two, it gives us the opportunity to identify gaps we wouldn't have seen otherwise. And number three, it gives us the ability to measure in terms of days of investment, how long it takes to actually exploit something. So an example there is, if I build the world's greatest security feature and then I hand it to the red team and they hack it in 2 days, I think that's objectively not the best security feature, right? Would you say? But if I can do one round of improvement and that jumps up to 90 days, that's something worthwhile. Before that, and for the vast majority of security vendors out there that are selling pixie dust and magic boxes, no, they don't have that kind of empirical analysis because it actually is pretty hard, right? It's like, I'll tell you this, most of the features that the red team hacks are features I design, and every time it's a punch in the gut. It's like, oh, I should have known better. But there's some improvement that comes out of that. Besides prevention in the platform, there's another place that we've started to use this process, and that actually the remainder of the talk, I'll kind of show you some of the use cases there. We at Windows have absorbed this assume breach mentality and past preventative security, I think, to the max. And the ultimate culmination of that strategy is Windows Defender ATP, which you've been watching the security story here at the conference. We describe this as a post-breach technology. And the reason is even when we're pretty good in this prevention space, you're still going to get hacked. You're still going to get, no matter how many mitigations I build, somebody's still going to get hacked. There's just far too much money involved, far too many resources, far too much innovation to prevent that. And while I admire platforms like Android, Chrome OS, and iOS because they have world-class security technologies, I think those are very secure platforms. One thing they haven't done is absorbed the post-breach mentality. And I'll give you an example, right? I think most of us think of iOS as a pretty secure OS, right? A couple billion devices out there, very few reports of security vulnerabilities. But just last year, full exploit chain through an SMS to a particular target attack. It's called the Trident attack. And the challenge with iOS is, how would you know that happened? How do you get a log off an iOS phone? How do you get a behavioral detection? How do you get a static detection? So they put all their eggs in the preventative basket, which hopefully, 10, 15, 20 minutes into this talk, I've proven to you through my own experience that is not so great. So when we developed a post-breach solution, we also wanted to make sure it was grounded in this same kind of attack modeling so that we could make sure that we were able to detect things that we were claiming we could. So if you're going to say you're an advanced threat protection product, you probably need to be able to detect advanced threats. And the only way you're going to be able to do that day one is if you've done a lot of offensive modeling internally with world-class folks. And so that's one of the things we did. So I'm going to now show you a couple of case studies of where we actually did some exploitation and what it resulted in on the detection prevention side. I've sort of talked about this ad nauseum, but I did want to hit on this. In the ATP world, we have this concept of what we call sparring. So why do we call it sparring? If you think about boxing, what do you do before the big fight? What did Triple G and Canelo do? They both sparred, right? They didn't just walk in there day one and say, I hope all that bag punching turned into me knowing how to fight. They did a bunch of practice rounds. And so that's precisely what we do in the ATP world is we utilize red teams, both folks developing exploits as well as folks doing operational security to simulate attacks on machines where we've connected, and anything we miss, we have a pretty specific goal on SLA to try to detect. So that is how we use this in the post-breach world. So let's look at one case study, and then I'm going to show you some exploits, because everybody likes to see exploits, right? The first case study is a device guard red team operation. How many folks in here have heard about device guard and virtualization-based security? All right, I would have been very disappointed if only a few hands went up. Our marketing teams worked really hard on that. The Microsoft OSR team, the Offensive Security Research team, had to red team device guard before it came out, right? This is a very big investment. It's sort of the crown jewel of Win 10 security. It's really an innovative approach to moving security to the next level. I'm a big fan of it, but we also needed to make sure it was delivering on the promise. And so what we did is we had the Offensive Security Research team essentially do a clean room operation to try to exploit device guard. And I'll just cut to the chase. We absolutely exploited device guard, not just once, but many times. But we did all of this early in the product. We found the vulnerabilities. We sat down with the engineering team. We fixed them. We did it again, and we did it again, and we did it again. And if you recall when I was talking about those KPIs, which is we start at n number of days to mitigate, and then hopefully the next round is n number of days, and we keep doing that until we think from an empirical standpoint that we're in a solid space. And so the OSR team built a particular chain, which I'm going to talk about because it later had some interesting results in the public. They built a chain which utilized a browser vulnerability combined with a kernel vulnerability to get into ring 0. And then they targeted a firmware vulnerability to get past device guard. So 3 different exploits. That would be a pretty substantial purchase on the open market. The first, probably the most interesting part of the exploit was a kernel vulnerability. This was present in the early versions of Windows. And one of the reasons I thought this vulnerability was interesting and kind of described to you what it's like to write an exploit is the thing you could do with this vulnerability is you could write a value anywhere in kernel memory. So you could literally send a message to the kernel driver and say, write at address 1234. That's pretty powerful from an attacker's perspective because they can do things like turn off security with that, turn off code integrity, change access controls. It's very powerful. We call that a write primitive in the exploit world. But what you didn't control was what the value was. That's kind of a bummer because if you just write a random value somewhere, most likely it's going to crash. But the interesting part of this exploit, and this is where I wanted to kind of bring you into what it's like to write an exploit, is that value was proportional to the temperature of the GPU in the machine. So what these guys on my team figured out is, if I can get this value above n, then I can use it to corrupt the length of another field, and I can use that field as basically a way to now write all of memory. So their actual exploit fired up the GPU, sent some shaders until it warmed up enough, and then when it warmed up, we took the value and overwrote it. So that's the kind of innovation that has to go into things like this. And that was a vulnerability we were able to fix and as well as add some mitigations for. But one of the particularly interesting parts of this exploit is where we eventually ended up corrupting after we got that sort of GPU right, we thought was a novel technique because we see a lot of these. Actually, Elias in the front row is like the biggest exploit geek on the planet. You could talk to him for years about that kind of stuff. But what we found is that the technique we thought was interesting, right? We developed something. And so we built a mitigation which introduced a very specific length check at a place in the kernel. And we shipped that in a version of Windows. And a couple of weeks later, our dear friends at Google decided that they'd found an exploit in the wild and that we'd only had a few days to fix it and that should have been sufficient time. And they just released that 0-day into the wild. Now, that was kind of a crappy day, but the bright side, the silver lining to that is the technique that was leveraged in this zero-day exploit by an adversary we call Strontium. So in the Microsoft world, we assign these elements to all of the different attack groups that we track. And Strontium, a lot of people, I'm not saying myself or anybody at Microsoft says this, but a lot of people associate the Strontium actor with the same folks who did the attacks on DNC. And so what happened with this is Strontium was using the exact same kernel corruption technique that we built the mitigation for. So Win10, although it had the vulnerability, back to vulnerability versus actualized risk, the exploit didn't work on Win10. And that was precisely because our team had basically traveled the same path probably as these Strontium folks, probably all read the same articles, had the same knowledge of exploitation, but we got there first. And that is a really good example where in practice this kind of mitigation and threat emulation can result. And not only did we build the exploit mitigation, but in ATP, we shipped multiple stages of detections for this type of technique. And so we were able to come out with a strong story, even though the exploit was put out in the wild by Google, we were able to come out with a strong story about how Win10 customers were protected. And one of the things I want you to leave here with is this is one of the powers of this 2 times per year release cycle is myself and the people on my team can get a lot of this stuff out to you faster. And we're really good, but we're, at best, we're often just ahead of the attackers, which means if you can get onto that latest version of Windows at any given time, our track record there is pretty stellar. So let's look at what this exploit looked like in practice. So what we actually did was we modified Win10 so the exploit could work, and then we used that as a method for attacking a machine, a simulated machine, and then we're going to play back some events in ATP to show you, just showing you the exploit doesn't work isn't a great visualization of the attack. So instead we're going to show you the stages of the attack and how we see it in ATP. So let's see. So this first stage is actually just a browsing to a zero-day exploit. So at this particular place, we obviously kept this on an isolated network. We didn't want that kind of stuff to go out there. But in the real world usage of this would have been a targeted direct link in your email. In most cases, the tradecraft of Strontium is to learn a lot about you, learn what websites you go to, register a very similar website, maybe 1 character off. And they're so detail-oriented that they'll often use in the link maybe a news story that's relevant for that day. So when you look at it, unless you're really looking close, you're not going to think about it. And since they're often targeting diplomats, then they will tailor this to that community. So you'll often see news stories and things like that. So when we click this, it's pretty silent in terms of the exploit, not a lot of visualization, but you're automatically redirected to a target site. Did I hit play? Yeah. So you're automatically redirected to the target site. You can see not much has happened visually, but in the background what's actually happened is there's been a flash zero-day exploit and a kernel exploit, and that kernel exploit's used to escape the sandbox, because otherwise they wouldn't be able to use that to dump credentials or gather access. And then you're immediately sent to the site that you thought you were clicking on. So that site in this case was Politico, which some people here may be familiar with. Most likely, I don't recall, but the attackers probably used Politico with a 0 or something very close so they could get you to click through and go through their site, hand you the exploit, and then send you on your merry way like nothing happened. Now, we're going to play back that same sequence of events in ATP and see what ATP saw. So immediately, we can see that ATP sees that there's a suspicious portable executable or an executable file dropped from Internet Explorer. How do we determine this is suspicious? Well, the cool thing is with the intelligent security graph, we can actually determine how often an executable is created from a particular process. So I'll give you an example. If you install an ActiveX control, a process usually gets created. If you're using old IE and you maybe have Silverlight or something like that, there will be processes. So we can't just say any process. That's bad, right? If any process is created and we start alerting, nobody's going to use our product very long. But instead, what we can do is say, this is the only time in the history of the world on our optics on 1 billion machines that we've ever seen this portable executable file created, and that probably means there's something bad that's happened. But that's a good example of how we're able to use that data. The second thing that we detect is anomalous change in privilege. So what does that mean? Anomalous change in privilege in this case is really obvious. The Internet Explorer browser is running in what we call a sandbox. That sandbox is, the way to think about it is, has the least privilege of any process on the machine. But in an instant, it went to a system-level process. And what was happening is the exploit, the kernel exploit, is copying a token from a higher privilege process, maybe WinLogon, maybe CSRSS, into the eProcess structure, the process structure that describes its privileges, and turning Internet Explorer from a lowly sandbox process into a full system process. Being able to observe that makes it pretty obvious that there's something wrong there. So these are two of the techniques that we were able, with input from red teaming and other sources, to create and get out there before the Strontium exploit, which means for Win 10 at the time, when this was big news, the exploit didn't work on Win 10, it was mitigated, and we had full detection. So that's a pretty good story, and that's all because we were willing to do some threat emulation beforehand. So this is just an example of the abnormal process anomaly. Of course, with ATP, you can kind of pivot across your enterprise. Often these campaigns will come in waves where they may send this to 10 or 20 users in your enterprise. So being able to pivot on that is interesting. We can see these are the actual Strontium payloads. The connection man is their implant. So this is all of their tools that are all visible. And you can see that they were actually targeting a URL for Politico that was associated with some troop movements in Syria. So like I said previously, pretty consistent with their approach to targeting diplomats. Now, that was a good example of a public event. Here's a pretty good example of, I think, Microsoft being pretty progressive in protecting our own network, and most importantly, using our own stuff and making sure it's good. So Microsoft uses ATP, Defender ATP. 80% of the detections on the Microsoft network actually are generated from ATP, but those are actually run side by side with a lot of other products. And one of the things that creates an opportunity for is it creates an opportunity for us to test our own products and how well they protect our own corporate network, which, as the cloud becomes more important, Office 365, that also means our customers' data. So we actually regularly have what we call the One Hunt. That's a play on the Microsoft One motif, which is we get all of the red teams or representatives of the red teams in a room, secluded somewhere on campus. Same time, we get all of the blue teams, right? People focused on detections using console security operations and IT security folks in a different room on campus. And the red team gets slid under the door. I don't know if that really happens, but it sounds cool. Slid under the door, a set of targets, and usually are really critical targets. And they're supposed to go after them. And the blue team doesn't know those targets. They just know there's a red team operation going on, and they have to find. So that's a really good event for a couple reasons. One is, for your operators, it teaches them how to communicate, how to work across organizational lines, how good they are at responding. Do they know the data? Do they know the procedures? Do they know the adversaries? Does this person know this part of the network? Right? It really helps you to iron out those kinks. For the red team, it's just fun. We're just hacking. But for the first time a couple of years ago, this had been going on, I think, several years with operational red teams. Because the trend is they're much more progressive than us in Windows, these cloud people. And so for the first time, I brought my team in and I said, what if we could provide you red team people with zero-day exploits? Huge smiles just appeared. And we decided it would be really good during this threat simulation if we could see if products like Defender ATP, if Device Guard, if all those things, do they hold up in practice? Do they really work for the purpose for which they were designed? And so doing this on the corporate network, I think, is the ultimate representation of us being really serious about this. And so that's exactly what we did. We put together the red team in a room who provided the operational folks with zero-day exploits, and we deployed them on the corporate network. So what we did is we were able to identify a vulnerability in a corporate web server and take control of that web server. We did exactly the types of tradecraft that attackers do all the time, which is we did a so-called water holing attack, which is You put something bad on a web page that you know important people visit regularly, and you sort of wait by the watering hole until you get a shell on their system. So we injected an iframe onto that site, and every person on the corporate network for that period of time who visited that in the browser that we targeted got exploited. Not only did they get exploited in the browser, but we also used a kernel vulnerability, so we had full system control. Once we had the system level token in the browser process, we did an in-memory only injection into WinLogon. So the important thing there is we're really sticking it to the blue team by not touching disk, because we all know, disk is a great place to have forensic artifacts and detection. So we're really using pretty advanced tradecraft here, and we use that to take control of the machine. Furthermore, the vulnerability that we used in this case was actually in the Chakra, or the JavaScript component of Microsoft Edge. I think the reason I'm showing this is I think this is progressive, but not only did we find the bug, but Chakra is on GitHub, and you can go look the bug up yourself. So we actually published the bug and the fix, and it's available there. You can see Jordan from my team, the OSR team published that. So that's the bug we used. And the exploit sequence, which I'm going to kind of jump through because it's fairly technical, but the concept of the bug was we corrupted a structure in JavaScript by finding basically what we call a use after free issue in the JavaScript engine. That allowed us to read and write arbitrary memory. We were able to utilize that to corrupt several structures and get sort of arbitrary code execution. We then followed that up. This is all in memory without ever touching disk. We followed that up with downloading a DLL from a remote server that held our second stage, which was this kernel exploit. And then once we had system using the kernel exploit, we pulled just a standard pen testing toolkit, which is the Metasploit interpreter, and that gave us in-memory execution in a pretty interesting way. So we'll actually show you a couple things. This is an interesting demo. So what this demo is going to show you is first that we actually have the exploit. We'll show you, popping, I think, Notepad at system, which is pretty standard. But we're actually going to show you the before and after pictures for ATP and how much it improved as a result of this exercise, which was a couple of years ago now. So in this first sequence here, we're just running the standard exploit. Hopefully it's running. Hit play. We'll hit play here. So we're running the exploit, and we're just going to show that it works by popping Notepad at system. We could have, executed anything we want at that point, but this is just a simple way to visualize it for you there. All that stuff in the browser is just various instructions that are used as part of the return-oriented programming chain. So we've got a system-level process running there. And now, what we're going to show you is ATP's visibility into this attack in just a second. I hope I know where that is. So this is the before and after for ATP, which is, in the first place, we never hit the disk. We go straight to kernel. We use a bunch of reflective techniques. This is early version of ATP before we had some of these sensors and IOAs that were required. And then afterwards, we implemented what we call memory sensors. And it's probably worth talking about what memory sensors are. As a result of this attack, we actually sat down with the kernel team who owns what's called the memory manager, which is a critical component in Windows. And we asked them, how can we get visibility into executable memory? Because executable memory is the key to doing in-memory attacks. We already had visibility into executable files every time a file is written in the system, but we want to see memory. And it wasn't available from any kind of public API or anything at the time, so we actually had to innovate with them to create a concept of reputation for memory. And the idea, and what you're seeing manifested here, the idea is when we did that exploit and we pulled down those DLLs into memory, Edge started looking funny. If you were able to look at it in a memory analysis tool, you would see Edge went from having just a few executable pages from JavaScript, maybe 1 or 2K at a time, to having megabytes of executable memory, which if you can profile with analytics or machine learning, you should be able to figure out. It's really weird that there's one Edge in the world that now has 2 megabyte memory slices. And so that's what we did, is we actually went out and built a concept of reputation on memory. You're probably Some of you might be familiar with this concept of file reputation, where you get a file that's never been seen before. It might be polymorphic malware. Well, the same principles apply to memory. We just needed a way to do it. So we sat down with the kernel team. And the second thing we did is, our red team, they love with glee really doing stuff that they know is going to throw off products of the blue team. This is what makes them happy at the end of the day. And so our blue team sat down and said, well, we can detect corruption of these kernel events. We can look at these different structures as indicators of problems, and we can send that up to the cloud and join it with telemetry to find these issues. And so what we went from is basically having very little optics onto this attack to afterwards having not only optics across the entire chain, which I'll show you here, but really making the red team nervous about the next year, because they had basically not only been stopped, but they'd been stopped durably in a way that they didn't know how to get around. So I'll kind of skip through that, but that's a pretty big win, is we now are able to, or I'll back that up a little bit. So without memory and kernel sensors, the exploit is pretty much undetected. And then with memory sensors, what you're going to see is we have memory anomalies, we have kernel anomalies, we see the cross-process code injection into WinLogon. So every single stage of the attack is now painfully available, and of course can be indexed with other machines. So this is really like a zero to hero kind of story. And you rarely see the situation when the shoe's on the other foot and the red team's like, oh, what do I do now? But that was definitely a situation here. And this is not an isolated incident. This is pretty regular in the ATP world. So the outcome is that we built a bunch of mitigations and a bunch of more durable detections from doing this very realistic simulation exercise. We're also able to hand the zero day to other teams so they can analyze it and improve different systems, cloud systems, all over the place in Microsoft. We've got different needs for that. And we're able to tune our sensors and improve it across the board. So there's a real measurable impact to both Microsoft protecting the corporate network, and then of course we extend this technology to you folks through Windows 10, ATP, all of our different services, and this is really one of the places where red teams are having a huge effect. Now, that was sort of the case studies I wanted to show you. Now I want to show you a bit more of the outcomes from a feature set perspective and how we approach turning all of this intelligence into mitigations. So the thing that we like to describe ourselves as having at Microsoft is vertical engineering superpower. What do we mean by that? It's very few companies you can work at, and this is the thing that makes me passionate about the company I work for. There's very few companies you can work at that have a compiler, a hypervisor, an OS, a browser, and then a cloud platform to put together. So when we think about mitigating something, we're not limited to one part of the chain. So for example, if I'm an EDR solution that's not part of Windows, I'm generally going to be limited to monitoring file events or trying to hook APIs or some of those other things. And obviously there's some folks that can bring some really great value there, but being able to sort of change the law at physics at any time and say, I don't like the way the compiler gives me instrumentation to block exploits. I'd like to redesign the compiler. That is true power. That's X-Men power there. And so we use this with regularity. When you look at our mitigations, a lot of times it's not just a change in Windows, it's just change in the compiler, the hypervisor Windows, some service that backs it, telemetry, right? It's really that vertical engineering superpower. So it's sort of critical to understand our thought process here and why we make the changes that we do. There's also huge benefits outside of security, just pure security value, which is when I change the compiler or I change a certain part of the operating system, it may have less disruption to the productivity applications you have, your workflows, and things of that nature. So when we think about mitigating software vulnerabilities, we want to look at the various parts of the chain. So the first stage is the core software vulnerabilities. That is the classes of vulnerabilities. You've probably all heard of buffer overruns. Some of you might have heard of use after free. But there's really an endless taxonomy that describes these different types of software flaws that over-caffeinated programmers sometimes introduce, unfortunately. So what we want to do in a lot of cases is to prevent those from being used in bad ways is we want to generalize the class of vulnerabilities and then think about how we can break that at the compiler, et cetera, et cetera. Those types of vulnerabilities are often turned into what we call generic exploitation primitives. That's a fancy way of saying they always want to get to the point where they're reading and writing memory. So this is like sort of the transition in state space that we like to reason about. And then the final part of that state space is obviously the payload. So the first part of our strategy is eliminating vulnerabilities. That's the prevention part I talked about. The second part is breaking exploitation techniques, making sure you can never get to the final part of that stage. And then the fourth stage of mitigation is if you were able to get through all of that and run your payload, then we want to be able to apply containment. So because of this, we think about our strategy for mitigation in a few ways. So we've got a strategy and a set of tactics. The primary strategy, I think, is very realistic. You notice there's no Oracle unbreakable statement there. The statement is, make it difficult and costly to exploit things. And we do that by eliminating classes of vulnerabilities, breaking the techniques that turn those vulnerabilities into exploits. If the exploits exist, we want to contain the damage through things like application guard and app container. And then finally, we want to use fast updates, telemetry, and post-breach to limit the opportunities and the damage from those particular exploits. So the pathways to arbitrary code execution are pretty simple. There's actually a very finite number of ways in which you can execute bad code. The first thing you can do is you can load a DLL. So that gives us opportunity to apply things like code signing, some of the features in exploit guard that prevent generation of new code. That's how we might stop you from generating new code pages. And then finally, you might need to hijack control flow or corrupt the way the process normally works and redirect it into your code. That's an opportunity for us to use technologies like control flow guard, which is in the field that's called control flow integrity. That's a place where we can invest heavily. So thinking about this very structured taxonomy gives us a place where we can constantly say, invest more here. We're doing well here. Let's move over. But we're constantly thinking in terms of these chains and how we can stop that. But breaking those things is absolutely critical. I'm going to kind of skip through this because I'm running fast. But I think the most important thing to understand, and I want you to take away from this slide, is Microsoft, when we're designing our mitigations, assumes the worst case scenario. We always assume that the attacker has a read-write primitive, which is basically the hardest thing to stop. We assume that they have JavaScript or some other interactive runtime. And we assume that they know the state space of the addresses. Why is this important? You'll hear many, many folks that'll come to you again, and there's pixie dust out there and magic boxes where they'll say, I can stop exploit X. But a lot of that is assuming the best case scenario, which means with a little bit of extra engineering work, an attacker can bypass. We can't really do that for a bunch of reasons, mostly because we've got a reputation to uphold, and I think our software is used in so many critical places that we owe it to our users to deliver. But it's important that, from a transparency perspective, that every time we're talking about a mitigation, this is the threat model and the worst case scenario in which we're assuming, and we design under those constraints. So there are 4 what we call pillars to stopping exploitation. And those fit into 2 categories. The first category is preventing arbitrary code from running. We do that in 2 ways, and all of these sort of pillars are implemented at full in Microsoft Edge. And the reason we start with Microsoft Edge is that's really where the battleground is. The browser is really one of the key places. So we prevent arbitrary code integrity in Microsoft Edge in particular in a couple ways. The first is we only allow Microsoft signed DLLs to load in Edge. So that means that even if an attacker can get an exploit working, can't really load the payload because it's going to be validated against a Microsoft signature. Great. So what does the attacker want to do now? If I can't load an image, I'll just call the memory allocator and I'll ask for executable page, right? It's exactly what the OSR team did in the One Hunt. So what we implemented in the last version of Windows, which is the creators update, is what we call ACG, or arbitrary code guard. And what we did there, I think, is pretty revolutionary. We prevent the browser from ever creating new executable code. Why is that amazing, and what's hard about that from an engineering standpoint? Well, the reason web applications, like you see in Chrome with V8, or Firefox with SpiderMonkey, or Edge with Shaka, the reason that we can run web pages so well at this point in time is that JavaScript is immediately converted into low-level code, assembly code. So when you're saying alert 1 in that dialog box, you're actually generating a couple pages of assembly code. So it's not really going to work well, and you're going to lose a lot of performance if you just stop new executable code pages from happening. Your performance is going to go down, I don't know, 10x, 50x, 100x. So that's going to be tough. And so one of the ways we're able to address arbitrary code guard and get that in place is we moved our JavaScript engine out of the content process, where attackers can't really tamper with it, and we shut off all code access for the actual content process of Edge. And what that means is when you're running Microsoft Edge now and an exploit occurs, all that the attacker can do is ask this secondary process for pages where we can validate it, and if it's a valid request, we can map things in. Attackers can no longer generate arbitrary code themselves, and that cuts off a vast number of attacks and forces them into essentially return-oriented programming. And return-oriented programming really says, I can't create new code, I can only jump around to different pieces of code and try to string that together into a payload. But aha, we've thought of that too. And that's where control flow guard comes into place. With control flow guard, what we did is at compile time, we had the compiler say, tell me all the valid code paths that the software developer said are okay. And we generate a map of those. And now when that executable is loaded by the Windows kernel says, give me that map, loads it into memory. And if that map is ever deviated from, it terminates the process. So what that means for the attacker is, since arbitrary code integrity is cut off because of this signing and this ACG, they are now going to go to full ROP, but they can't do that because they're going to end up taking paths that the developer never intended, and the kernel is going to shut them off. So that is a good example of how, back to that mapping and how we think about mitigating attacks, we've sort of thought about all of these paths, and we're constantly turning the cranks. Now, I'm talking about this in a very holistic kind of defined way. There's obviously lots of creases and crevices and cracks here that are still possible, but from a strategic standpoint, this is ultimately what we're looking to do. I'm going to kind of skip ahead in this just because we're running out of time, and I've touched on it, but ACG, like I said, is something that's applied to Microsoft Edge in most of our VM worker processes by default, as is CIG. Essentially, there's some compat issues that are potentially possible with these technologies, and so we want to apply them first on the places that can get the most value, which is protecting your VMs from being exploited, both in your local on-premise deployments as well as in the cloud. And then we are, with each release, applying these more and more to the platform. We hope to get to the point where arbitrary code execution just isn't possible. I'm going to skip through here. So there's one particular piece that I didn't discuss, which was that missing box in the 4-pillar strategy. And that is CFG, or our control flow guard, works for what we call forward edge code execution. That's a fancy way of saying we cover jumps and calls, basically forward paths. But if you're familiar with computer architecture at all, you know that every time you execute a routine, you call a return and you pop off the stack and you go back to where you were called from. That's what we call a rear edge control flow transfer, very fancy terminology. Why is that critical? It's critical because if you can target the stack, control flow guard doesn't put any constraints on you, and so attackers still have the opportunity to do ROP because we've only done 3/4 of our strategy. And this is one of the places that our friends in the kind of red team had actually beat us up, right? So we got us defenders have 3/4 of our strategy. Red team people are like, well, I'm going for the stack. It's still available. And so this is actually where a bunch of us sort of got in a room at one point and said, we've got to do something about a return of just protection. And it's a very hard problem. If you look back in 20, 30 years of security research, you'll see lots of research around what's called a shadow stack or various mechanisms for protecting the stack. And we worked first with Intel and other hardware partners on baking stack protection directly into the CPU. And we actually achieved that. It's coming in the near future, and it's called Control Enforcement Technology, or CET. So the thing I told you previously, the map that's loaded by the kernel, that will eventually, at least for stacks, be the kind of thing that the CPU will maintain. So that's pretty awesome. That's kind of the highest level of durability. But the issue was the red team was still hacking us, and we're a couple years away from that. So one of my proudest moments of my career is we came up with this thing called return flow guard. And again, a lot of these technologies require compiler, virtualization, so they usually require a huge number of people. But this is a case where the attackers, the red teams, got together and said, we're going to be agile, we're going to do this on our own, we're going to change the compiler even if we don't know how to do it, we're going to do this as a security community. And so we actually came up with a mechanism of a shadow stack that protected these rear edge control flows. And the simple way to think about it is you get two copies of the stack. The first is the real stack, and the attacker can change that. The second stack is hidden somewhere in memory that the attacker can't find easily, even through brute force or corruption, and is hidden from sight. That's why we call it the shadow stack. And so by having these two copies of the stack, even if the attacker can corrupt the standard stack, the one they can find, and use that for return-oriented programming, they can't ever find the shadow stack, and if they do modify it, it would result in an access fault, and the process would crash. So we think, hey, we're onto something. We think we've novelly designed this. And this is where we need to keep red teaming realistic. There was one problem. The red team that created this feature also found a way to durably break it. So this was really interesting. If you're familiar with the Windows Insider preview process, one of the cool things that I think people miss is you're actually seeing us incrementally develop things. So when I write something and check it in, I'm not actually sure it's going to make it to the final product, but you see it in the Windows Insider previews. So with Return Flow Guard, we started developing it, we're checking in, we're doing pieces. Our friends from China that win pwn to own all the time, they're saying, oh, D-Wizzle, we can see that you made this new feature, this is awesome. And I'm getting asked about it and all of these things, and people are starting to get excited, even though we haven't said anything, because they're watching us in the Windows Insider preview. But the bad news is, one of the same vulnerabilities we used in One Hunt, we actually used and applied our threat model to RFG. And guess what happened? We found a critical design flaw in Return Flow Guard. We found a design flaw that really meant if we apply our principles in that threat model and that durability I talked to you folks about, we can't ship this. So we took it out. And even though in some ways this was a massive failure because we designed something that didn't work, but I also told you this is a 25-year-old computer security problem that's hard to solve, and in some ways maybe we're arrogant for thinking we could do that, we used our own principles of red teaming and really pounding on something, and when push came to shove, we took it out because it didn't meet our standards. And I hope our failure is evidence to you folks that we're very serious about delivering this, and even something we'd work 6 months on and sort of get some public embarrassment about, we would take it out if it doesn't meet the quality level. And I think that's what we did here, and that was a really proud moment for us. So, moving on and kind of closing this out, we've now built up this pretty good corpus of protection features, and a lot of this I went probably even lower than would be normal outside of security conference circles, but I think in the past I've gotten good feedback around people expressing their interest in this low-level stuff. But a lot of what people were looking for is the ability to sort of use this at their own discretion. So a lot of the technologies I've talked to you about are sort of hand-curated by Microsoft, and we're applying them to specific products. But you're probably asking yourself, like, Dave, how could I use that to protect my old versions of Word or Java, et cetera? And that's where Emmet, our enhanced mitigations toolkit, had built up a cult following, because there's a big set of folks who wanted extra security, maybe on older products, older software, and some of these mitigations that I showed you weren't on by default for various reasons. And so people turned to Emmet as a way to control these policies, and it became very popular. The issue with Emmet is it actually started off as a side project, so we really never designed it to be supported. And it built this cult following, but for a bunch of different reasons, performance, reliability, other things, we could never build it into the product. And so we were able to finally, with this upcoming fall creators update, which will be out here shortly, we're able to bring that configurability that people loved about Emmet, but join that with what I would say are the superior performance, reliable mitigations in the platform. And you can now configure, just as a standard user on any old version of Win 10, as long as it's got the fall creators update, mitigations to your heart content, and there are a lot of them. Some of the ones I covered today, some I didn't cover. So exploit protection, a lot of the stuff that was taking you down to the sort of C level, you can now configure as you would. And of course, we've got PowerShell, we've got group policy, we've got MDM for all of this stuff. And that's pretty critical. We also introduced 5 different mitigations that were never in the original version of Emmet that are there for you to apply to your legacy processes. So if you've got an old version of Java on your network, not that I advise that, but if for some reason you absolutely have to have that, you've got some options here for turning on some things. And so after years of clamoring, I think we finally delivered the Emmet inbox that a lot of people had been asking for, and we also gave a little bit more. So hopefully you're excited about that. I'm gonna skip through. So in the wake of, I've talked a lot to you today about browser security, especially user mode stuff, but in the wake of WannaCry and NotPetya, there's been a lot of talk about kernel security. So hopefully you've heard by now, Win 10 wasn't vulnerable specifically to the version of the various shadow brokers released exploits that were used by both WannaCry and NotPetya. And that was actually a result of a lot of the hardening you've seen today being done specifically in the kernel. But this is a place where I'm really proud to say I think we're actually a bit ahead, which is the exploits that you saw were probably circa 2014 or 2015, depending on who you ask. And what we've seen is avid research community is actually taking those exploits and push them forward. And so it's now becoming more critical than ever in the wake of these that the kernel is as protected as the browser, right? There's been a big focus on the browser with so much there, but this is really changing the dynamics of what we think is possible with kernel attacks. And this is where virtualization-based security, or VBS, is really advantageous. So thinking back to that set of 4 critical pillars, the ACG, that is the ability to not create any arbitrary code, CIG, the ability to not to block any unsigned code from loading, and CFG, control flow guard, the ability to enforce forward edge control flow, are all available in the Windows kernel if you turn on virtualization-based security. So Windows 10 today, with just software mitigation, stands up to Eternal Romance and some of these other exploits that were used, but we think this is a great path to future-proofing, is if you can enable virtualization-based security, you get all of our critical strategic elements for the kernel just by turning that on. So finally, the vast majority of what I talked to you about today is what we call mitigation, or stopping those exploits from happening. But if you recall back in the sort of strategy that I laid out, we don't just focus on preventing bugs or stopping exploit techniques. We also want to isolate the damage, and we've been hard at work there. So we're continuing to invest in our improved isolation technologies in 2 ways. One is in regular Microsoft Edge, we improve the sandbox. This is where I get to use my sales pitch. Now with 90% less attack surface. So we actually took the attack surface of the Edge sandbox down to very few calls. We reduced the attack surface by 90%. That's 90% surface that someone can use to find an escape, and that's really important. There's been a lot of talk about, in particular on the security community, around Microsoft Edge versus Chrome, where Chrome takes a more isolation-centric approach, and maybe Microsoft Edge takes a more mitigation-focused approach, and I've displayed some of that here today. But I would say that we're very balanced in the sense that we're investing in the software sandbox, and of course, something near and dear to my heart is Application Guard, which is our virtualization-based isolation solution. This is where we took the operating system and we shrunk it down to a tiny little operating system that is just tailored for running Microsoft Edge. In fact, it's so small, if you're familiar with VHDs, like if you've done anything with Hyper-V, it's an 18 megabyte VHD. Entire operating system fits in 18 megs. And one of the reasons we're able to do that is we invented a new container technology. And this container technology does a couple of things that are interesting and that are different than Hyper-V as you know it. The first thing is it shares memory with the host. What that means is when you start up the VM, if it needs to load kernel 32 DLL and that's already in the host memory, it will just hand it to the VM. That's one less DLL that application guard needs to carry around. And when you multiply that across the entire operating system, that's how you get down to 18 megs. It's basically some extra registry. The other thing that's really cool is we have an integrated scheduler. That's fancy talk for saying if application guard's running and you switch to Word, it's deprioritized and potentially suspended. And so you're not chunking up battery, wasting memory, other things. If you've ever run VMs on your machine, and I'm one of the people that do that, this thing's running hot right now and spinning fans. And it's because the Hyper-V scheduler isn't integrated. Another way to think about this is we've invested so heavily in the container technology around WDAG that it's almost just like a process or job object. It's just another unit of execution on the operating system. And that's really going to set us up to do some great things. The final thing I'll say here is we have been really interested in testing this kind of approach of sandboxing versus remote code execution mitigations. So my red team actually went and exploited Google Chrome. We just released some information about that. That's here in a tweet. And the goal there was not to, sort of create some rivalry with Chrome or anything like that. The goal was to learn how do these strategies work in practice. Back to my original point that I hit on you is this has to be empirical. It has to be based on fact. So we said, let's go exploit this and see how it works in practice. And I can tell you it's a very good and secure browser. But of course, we also learned a lot. And these are the kinds of principles that we can bring back and improve Edge. And with that, I've yammered on for quite a bit of time. I thought I would just show you a demo that sort of illustrates how we use attacking application guard and how isolation works in process. So hopefully the demo gods are with me. This is actually a pretty complicated demo. I'm not on the screen anymore. Your PC can't project. Do I need to hit a switch or anything? Doo-doo. I have an idea. There you go. I got it. Sorry about that. So what you're going to see on the left-hand side here is the handy-dandy all-purpose exploitation tool called Metasploit. And I have it set up, actually, with this command here, listening for a successful exploit. This is going to give me a tunnel into anything I exploit, allow me to have a command shell, take screenshots, dump credentials, order a pizza, you name it. On the right-hand side here, I actually have a virtual machine running Windows Defender Application Guard. And you can see it's very similar to the native Microsoft Edge. There's just a small visual component in orange that says you're running in a virtualized environment. But this is actually a fully separate, hypervisor-separated operating system that should withstand any attempts, even a kernel-level exploit attempt. So what I'm going to do here is simulate what it would look like to get a spear phishing attack, very similar to the Strontium attack I referenced earlier. So of course, we've been offered to redeem a prize, which we will always, of course, click on. And because we've set the application guard policy in our VM, it automatically opens in the virtualized environment. And what you just saw is a live demonstration of a zero-day exploit that combines Edge browser vulnerability with a kernel vulnerability. These have actually been addressed, at this point, but this is a good example. And we have a session, an interactive session. So we can actually just change directories into users. Oops. CDC users. Oh, sorry, I missed a command. Sessions dash interact with one. Now I can change directories. So in this case, I'm playing the attacker. I want to look through and see what kind of sensitive information is on this machine. I'm assuming I compromised a full host, but what do I actually see up there? Container user, container administrator. I'm in a container. Now, here's the interesting thing. Is that because I don't have privileges, right? My exploit combined a remote code execution with the kernel bug. I should be able to do anything I want in this machine. So when I call get UID, I'm actually running at system. I can now, because I'm running at system, I can try to use Mimikatz. I can maybe dump some Kerberos tokens. Again, you see in Kerberos, the accounts that are available are WDAG utility or container administrator. So I'm actually fully containing an environment. So what you just saw is really a $500,000 worth of exploit that's fully contained, that prevents access from the host, that makes sure that credentials and documents are not available. And so it's really the highest kind of form of isolation that we have and something that we think is really innovative. So with that, I'm going to close out. So the conclusion that hopefully you'll take away is this work that's combining exploitation strategy with a heavy investment from the red team side is actually having a measurable impact. And it's apparently having a measurable impact on my machine as well. It's having a measurable impact. Exploit rates are dropping while the vulnerability rates are rising. So that means even though there's more opportunity to attack, there's less people being attacked. And we take that as a badge of honor and something we're very serious about. And if you're curious how you can help or learn more, we encourage you to look at some of our bounty programs. So we put multiple bounties up, whether those are vulnerabilities, exploit techniques, mitigation bypasses, any of those things. We pay up to $250,000 for the right vulnerability report. The other thing I would say is look towards moving to the latest version of Windows. We think that's the most secure expression of Windows. And in particular, if you're a Windows Insider and you're running our previews, love to get feedback on the security features and how they're working with your environment. And with that, I'll let you go. Thank you very much.